So I've got three great speakers for you today. Felix Pollock, our first speaker, began his physics career at the University of Oxford in the UK, not a bad place to start, and completing both his undergraduate and postgraduate studies there. He graduated with a PhD last year and came here to Monash to work with Cavan Modi. Felix's research looks at quantum coherence in biological systems, as well as open quantum systems and master equations. I would particularly encourage you all to read his recent article on the Conversation website, which describes the latest developments in quantum physics. It's up to you if you get into the climate change debate underneath. Outside physics, Felix enjoys Eastern European history, culture and linguistics, and his greatest passion in life, after physics of course, is food, cooking and eating it. Please welcome Felix, who is talking on the topic, the Quantum Zeno Effect, how curiosity can save Schrodinger's cat.
Thank you very much. Okay, so today I'm going to talk to you about what I think is probably one of the more interesting and less well-known aspects of quantum theory, which is the Quantum Zeno Effect. And I'll tell you a bit how you can use it to save Schrodinger's cat. So I should make a disclaimer first that despite all evidence to the contrary, no cats were harmed in the making of this presentation. I'm actually a theoretical physicist, so I'm not allowed into any laboratories where I can do animals harm. So what is the Quantum Zeno Effect? So it's named after a paradox that was first allegedly introduced by Zeno of Elea in the 5th century BC. So he found it strange that when you look at an object in motion, such as this arrow, which is in flight, that you can look at it at any instant, and at that instant in time it will appear stationary. So I can look at the arrow here, and if I just look at that instant in time, it appears stationary. If I look at it at another instant, it will also appear stationary, yet somehow it moves between the two. Between the 2 points in time, it moves in space. Now, it wasn't for another 2,000 years or so that we came up with the answer to this, or the solution to this paradox, which is calculus, which essentially means that the arrow moves continuously through time. And today it seems a bit nonsensical, this thing. But it turns out that when it comes to quantum mechanics, Zeno is actually pretty prescient. Because in quantum mechanics, it turns out if you observe the state of a quantum system at a given time, it actually changes the course of the system's evolution. And if you do this in the right way, if you look quickly enough and strongly enough at the quantum system, you can actually freeze its evolution. So if you really do know the state of this quantum system perfectly, at all times, it will never change. So to make an analogy with a popular idiom, in quantum mechanics, the watched pot really does never boil. So what does this have to do with cats? So Schrodinger's cat is a pretty well-known paradox from quantum physics. I imagine many of you will have come across it before, but I'll just go through it again briefly. So the idea, or the paradox, is that in quantum theory, we expect things to evolve into what are known as superpositions, where where a system can be in different classically allowed states, such as the cat being alive and dead, at the same time potentially. So I'll just quickly run through the setup of the thought experiment that Schrödinger proposed. So he said, start with a box with a cat in it, and then put the following device inside, or ideally get a hard-working graduate student to put the following device inside. So in the box with the cat is a vial filled with poison gas, which can be just broken, releasing the gas and killing the cat by this hammer, but only when a detector in the other side of the box detects the presence of a photon. So in with the detector, we put a radioactive atom, which is not to scale here. And we know that at some point the atom can decay, releasing a photon, causing the cat to be killed. So we can run this thought experiment many times. So where we put in a fresh cat with a new radioactive atom, we close the box, we wait for some time and we open it, and sometimes we find the cat's alive, and sometimes we find that we need to replace the cat. So nothing particularly strange so far, other than possible animal rights abuses. But as I said before, quantum theory predicts that systems will actually evolve into these superposition states, where the system where the system in this case is the whole box with the atom and the cat, can be in multiple classical states at the same time in some sense. And we really do believe that all physical systems behave according, well, most physicists really do believe that all physical systems do behave quantum mechanically in reality. So we really do believe that they will evolve into superpositions like this. So why don't we see these superpositions around in our everyday life? I mean, you never actually do see half-dead cats wandering around. And the reason is actually quite subtle, but goes something like this. It turns out that actually, if you were going to make a measurement of the box without knowing what the state of the atom was, so if you measured everything in the box except for the atom, you would only ever be able to get outcomes of your measurements which were completely consistent with classical physics. So as soon as you ignore some of the information that's in this superposition state, the rest of your system appears to be classical. So the system that you're ignoring doesn't have to be the atom. It could be some other part of the universe that's interacted with this box. And as soon as that part of the universe interacts with this box, as soon as we ignore any information about it, we can only ever find the whole box in one of these two states. And this is true for any macroscopic system or any system at all. Once it's interacted with something else strongly enough, then it will, if it's large enough, will appear completely classical. So anyway, let's move on to how the Zeno effect can actually save the cat. So if we run Schrödinger's thought experiment many times, and we wait for different periods of time before we open the box and collect some statistics, we can plot the probability of finding the cat alive, or equivalently the probability of the atom not having decayed as a function of time. And it will look something like this. And you can see at long times that the probability decays exponentially, and that's just due to the fact that this atom is decaying into a large environment, and we get, this is the standard kind of law of radioactive decay. But actually something interesting is going on at very short times. And at very short times, the atom won't have had time to interact with the full space of the box, and we'll get some more interesting complicated dynamics. And in general, quantum systems at short times evolve in this complicated way. But what we do know is that all quantum systems at very short times have to evolve in the following way. So if we look at the probability of the state being the same, so that in this case the atom not having decayed or the cat still being alive, at a very short time, it always has to start from 1. So if the cat's alive at time equals 0, or the atom hasn't decayed at time equals 0, we know, according to quantum mechanics, that the probability of it being alive at some short time later will always behave in this way. It will start off at 1, and it will curve down in this convex fashion. So this is just describing what the probability of measuring the particle or cat being alive looks like after a single measurement at a single time. But what happens after we've made the measurement? What happens to the probability after we've made the measurement? So it turns out if we measure the cat to be alive at a certain time, or the atom not to have decayed at a certain time, then we know that actually it has to be in that state where it hasn't decayed, and it will start evolving again as if we just reinitialize the system. So if we make a measurement, then there'll be some small probability that it could have decayed before. But if we measure it the cat to still be alive, or the atom to still not have decayed, then it will evolve again in the same way as if we just started it from that time. And we can do these kinds of measurements again, and you can see that each time we make a measurement, we actually increase the probability that we find the cat alive, or the atom not to have decayed at a later time. And we can make these measurements more and more frequently, and we'll see that as we make the measurements more frequently, the probability of finding the cat alive, or the atom not to have decayed at a later time, increases. And we can make measurements so frequently, so we can look at the state of this atom so frequently that we actually preserve the life of the cat indefinitely, or at least we preserve the life of the cat other than through natural causes indefinitely. Okay, so this is how curiosity can save Schrödinger's cat. But you might be asking, why is this useful? So it turns out that if, as an experimenter, you actually only have access to one side of the box, which has the atom in it, and you don't actually know what's in the right-hand side, you can actually use the Zeno effect to learn something about what's on the right-hand side. So, and this is, so it could be a cat or it could be something else, including something perhaps useful that you might want to know about. So it turns out that as I said, if you make measurements just on the atom, then you can actually learn something about the state of the atom's environment, or in this case, the right-hand side of the box. So if we plot this probability again as a function of time of finding the atom to be in its non-decayed state, then we do something to the atom. So we make a measurement which is not complete, which doesn't give us all the information about the state of the atom, but only partial information. Then what we do is we don't keep the atom in the same state, but we do change how it evolves. We do change the probabilities. And it turns out that the way these probabilities change depends in a very precise way on the state or on the environment that the atom has. So in principle, by making these weak measurements on the atom and then doing these later strong measurements, we can actually find out something about the atom's environment. So this could be, and this is not restricted to cats, we could actually have some complicated molecule or something that we might want to learn something about in the presence of this atom or any other quantum system. So there we go, that's the Quantum Zeno Effect and how we can save Schrödinger's cat. Thank you.